We've considered a hierarchy of methods for solving ordinary differential equations. So we started with Euler's method, we then to second order methods, the midpoint method and Hoyne's method. Finally, last time round, we looked at the Runge-Kutta fourth order method, or RK4 as I will term it. RK4 method, if you recall, requires making four estimates of the slope of our solution at various different points across the interval, and then combining these four estimates in a particular way to make an update from yi to yi plus 1. In a single step, the error is of order h to the fifth in the RK4 method, and as we've seen in other cases, if we look at the global error, it scales like order h to the fourth. And that's what happens when you take multiple steps to go from some starting condition all the way to some ending condition. One might ask the question, isn't fourth order accuracy sufficient? Well, the answer of course is no. I'll show you a few examples of that when we get into the workshop. So, how do we improve the accuracy? Well, let's go back to integration. Previously, we used Richardson extrapolation when we calculated integrals to improve the accuracy. And the basic idea is, and I'll give you an example here of the trapezoidal rule. If we do an integral with a step size of h using the trapezoidal rule, the exact integral I is equal to our trapezoidal rule estimate with a step size of h plus a series of error term. The leading order error term is the ah to the squared. So this method is order h squared. If we calculate the same integral, but now we use a step size of h on 2, we come up with an exactly equivalent expression, except now h has been replaced by h on 2, so we can see that the ah to the squared error term up here has become ah squared on 4. This then allows us to combine these two equations to remove this term here, and it's very easy to show that the exact integral is equal to 4/3 the trapezoidal rule estimate with the step size of h on 2 minus 1/3 the trapezoidal rule estimate with the step size on h, with an error term now, or a leading error term, which scales like order h to the fourth. The idea of using Richardson extrapolation for ODEs is identical to using it for integrals. So, as an example, we will consider a single step of the RK4 update of an ODE. We're going to write this RK4 update with a step size of h as a function here, RK4 of h. Basically, this thing here represents calculating that K1, K2, K3 and K4, and then updating yi plus 1 is equal to yi plus a whole bunch of stuff there. So this represents the process of doing all of this. So the exact solution of the ODE at y of t plus h can be written as y of t plus h is equal to our RK4 estimate with a step size of h plus a series of error terms. And as always, we're interested in the highest order error term, this ah to the fifth. And a is some constant coefficient, or some coefficient that we don't know the value of. If we were to halve the step size and take one smaller step, we would see that y of t plus h on 2 is equal to RK4 of h on 2, so that's just taking one step size of the RK4 method, one step of the RK4 method with a small step size, plus again a series of error terms. But now, again, h has been replaced by h on 2, so we end up with ah to the fifth on 32 as the leading error term. If we were to now take a second step, in other words, go from y of t plus h on 2 to y of t plus h, we could write this as the exact value is equal to twice the RK4 step using a step size of h on 2 plus some error terms here. So the ah to the fifth on 32 is the error in one step, but because we've taken two steps, we need to multiply it by 2. So that's where that 2 comes from. Just simplifying that then, y of t plus h equals RK4 of, now I'm going to write this as twice h on 2, it's a little bit of an imprecise notation, but I think you know what I mean. It means taking 2 steps of h on 2 plus ah to the 5th on 16. This is now the leading order error term if we take 2 steps of h on 2. So our original estimate using a step size of h is given by that equation there. What we now want to do is we want to remove this ah to the 5th error term. We're going to use these two expressions to do that. So let's just write them out here, equation 1 and equation 2. If we multiply equation 2 by 16 times all of that, it's going to get rid of that term there. And then we subtract equation 1, we end up with 15 y of t plus h is equal to 16 times the RK4 estimate using 2 small step sizes minus the RK4 estimate using a step size of h minus a new error term which now scales like h to the 6th. So we have removed the h to the 5th error term. Then of course we just divide this by 15 to get rid of that term there, and we come up with the final solution. Y of t plus h is equal to this expression down the bottom here. Step sizes of h on 2 and a step size of h. This 6th order scheme could in theory be used to create higher order schemes again in exactly equivalent way. We're not going to do that here. We're going to say 5th order is as far as we want to go. But we are going to use additional information that comes out of this Richardson extrapolation approach to try and make some estimates of the error in our solution.